오케이. 이 카메라를 자네들한테 비추니까 좋네. 내 얼굴이 아니라. 오케이. 자네들. 오케이. 자, 외국인 학생. Any foreigners? You? Do you understand some Korean? Any others? Do you understand some Korean? Okay. Any foreigners who doesn't have any idea about Korean? 없어요? 그럼 한국말로 강의할까? 네. 그렇게는 안 되고, 이게 물론 여러분들이 영어로 하면 이해가 어렵다는 거 알아요. 그러니까 자주 질문을 하세요. 그리고 내가 되도록이면은 중요한 포인트는 한국말로 강조를 할 테니까. 네? 뭐 영어 수업도 중요하지만 더 중요한 거는 공부를 해야 될 거 아니에요. 맞죠? 아니, 공부를 할 때 여러분들이 이해가 돼야 되는 게 중요하니까. 오케이. 근데 이게 녹화가 되는 것도 많은 학생들이 또 보기 때문에. So today, what we would like to do is again get back to a 3D beam and learn more about the 3D beam, especially torsions. Okay, torsions is a topic we're going to study using 3D beam and compare with the theory we studied, especially on thin wall torsion, thin wall shafts. Okay? This 3D beam, this tool is very powerful. You can use this tool to solve many structures as long as the structure is a slender member. Slender member means it's a longer compared to cross sections. So if you open the 3D beam, you will see this screen, main screen, and there are steps for materials. Okay, material, you can define your own materials. That's not difficult at all. There are many different material properties which you don't have to pay much attention. Just pay attention to stiffness and strength. That's all you need to do. So you can do many different material. Now you go to a laminate, and laminate again. Each shell or each thin wall can be made of laminations. So you can have many different layers. Layer 1, 2, 3, 4, almost as many as you like. But here, if the thin wall made of only one material, you just have one one layer. We call one layer, just one layer, and material steel, and this much thickness. Okay, please remember this thickness. And now this laminate is called steel. Okay, it's steel. That's how you define the laminate. And now these sections, you define the shape of the sections, and go to these sections, and you can choose any sections you like to define. Can be any circular or elliptic or a box or many structures. So this is a very critical step. You define where you define the cross sections. Once you define the cross sections, and you can go and so let's do here to define again a circular cross sections. So to define the circular cross section, you need a 0, 0. That's the center of this circle. And now, what is this? This is the laminate, name of the laminate, which you want to use to make this circle. So each laminate is called laminate steel, which you already have, right? So this is the one. And number of division is when you make a circle, you has a number of divisions. How many divisions? 여기 이름하고 날짜 써서 출석 불러요. 수업에 딱 2번 부르는데 빠지면은 끝이에요. 자, so this will have a 24 divisions, and this is very important. And radius is a 0.25, x radius and y radius. So I will show you how it shapes looks like. Remember, oops. 이게 뭔 일이야? So we went through materials and laminate, and again the section is important. And let's try to define a circular cross sections. And by the way, you can create your own worksheet, such as you can copy and make your own worksheet, so that, for example, say class or your name, whatever you like to do, and you can play with it and you can save it. So next time you can come to this point and you can do anything you like to do. So here, so 24 means that when you create the circle, you divide into 24 divisions. Again, when you define the section, this length has no meaning. Okay, it just show you so this is the shape we just generate. And also if I click this known number, there is a 1, 2, 3, 4, 5, and then up to 24. Why? Because we wanted to generate 24 a division, right? Here is a 24 divisions. Of course, you can generate as many as you like. The more you generate is a better accuracy. And so, but too many, it takes simply too much time. And now, let's say you somehow generate a 5, and of course, you generate 5, but doesn't look like circle, right? So again, you have enough number of divisions so that this can make a circle. Okay.
기준 같은 건 따로 있나요? 그냥 육안으로 봤을 때 서클이 되죠.
Right. There is no such a strict rule to make a circle. As you said, look like the circle is kind of okay. You know, the reason I'm going to emphasize again, the tool is based on all the discretization. We have to divide them. We have to line, we have to divide. In analytical solution, we always use a function, smooth function. It's like analog. But when we use a computers, we need to discretize. So it's like analog versus digital. So how fine we have to divide? Let's say you listen to music from an analog signal or digitized. If you digitize two chords, the sounds doesn't look like good enough, right? But again, it's not a strict rule. 그냥 이쪽으로 해. So there is a no strict rules to make a circle, but it's important to have a fine enough, okay, to make a smooth one.
어제처럼 만약에 사각형 단면을 만들 때 그 4개의 점을 찍었잖아요. 그러지 않아요. 서클로 하고 4개로 디비전을 4개로 해도 사각형이 만들어요.
Not quite, not quite, because when you make a box, which we already well, we don't have it, but let's say this is the a box. Okay, box, and this is a box, right? But as you can see here, even though this is box, we have a 1, 2, 3, 4. We have a divisions. We have a divisions for each edges, right? 1, 2, 3, 4, 5. So this is the how we divide each edge using this number of division. This is number of division is 4. For along this line, we have 1, 2, 3, 4. This way, 1, 2, 3, 4. So it's a different. If you choose just 1, 1, 1, 1, yeah, as you said, just like that. But it's very not accurate. Okay, so. So again, there is no such a strict rule, but that number of division is kind of based on the experience. Okay, so this is how we make a circle. And now I'm going to assign the task today. Would like you to each group and to explore this kind of a problem. For example, our group, we divide into 10 or 20, and this is the how much error, how much different. That is a very interesting study. So when you do a group task, this is the kind of case you can study together. I like to assign a big task, but within each group can discuss and generate some interesting results. Okay, that is very important capability. You as engineers, it's easy to do, just easy to do some is assignment. Anybody can do that, but you define the problem and agree, and it comes to a that is the very interesting. Okay, so now we generate, but please remember this radius. 0.25, okay? 0.25 is a radius we consider. So you have an imagine 2.5. What's the unit? All meters, okay? So 20.25 means this much. I mean, 0.5 diameter is this much. What was the thickness? we forgot the number, but it was very thin, right? So we have to remember that's very thin. Or we can, let's say we can, see, this is the thickness, 0.0004. So it's a 0.4 millimeters, 0.4. Say, let's say 0.4. Let's try to make a 1 centimeter. It's still good, right? This is this much and this much thickness. It's still considered as what? Thin wall structures. So how thin is the thin structures? Again, there's no strict rules. Say 1 to 10 ratio can be easily considered as a thin. Once we consider as a thin, the theory becomes very, very simple, right? Okay, so let's try to have a 0.01. We can do that, and let's get back to here. We don't need to go back and section and regenerate it because all the database has been redefined, so we don't need to. Actually, what we just did it was to generate this geometry. Okay, it's important to understand. Once we generate this one, what we have done is to we have to do it again. Get 20. 20. We want to generate the 20. So now we have a 20, and make sure that it has a 20, and then that's what we have done. And now what we have done here is nothing but generate this section dB. Section dB here laminate see all 1, 2, 3, 4, 5, 6 and so on, and this one. This all the data was stored in section dB. See, laminate 1 is the key point 1, 2. This is a 1, 2. This is a laminate. Here is the and we have a 20, right? 20, and that 20 is from here. This is a 20. So we have a 20 sectors, and you have a 20. What is this? So this is the information about the section 1. And here we have each key point. For example, key point 1, coordinate is a 0.250. Remember the radius is, we set 0.25. So this is the a coordinate of this one with respect to a 0, 0, 0. So this is the one. Just for the purpose of the confirm, we plot them. And this one is the so this is the circle we just generated. Okay, this is a circle. Of course, there is a one line is missing. the reason is that we just plot the points. So anyhow, what we have done is to nothing but generate this section 1. Okay, very important. This information, section 1, has all the information about this section. We have what's the laminate, what's the geometry, and this laminate has a material and thickness, right? So this is all about the sections. Of course, you can define another section and another section. And now if you go to a geometry, you can, not this one, geometry, and say you have a point 0, 0 and 10, 0. Remember, this is x coordinate. This is the line, and this is the we divide them into 10, and this is the point 1. I mean the 1 and 2. So we generate this one. We have a 10 divisions. Okay, but it is important that this looks like just one line, right? But keep that in mind. It has all section as a circle. It's not shown here, but it has a circle. The circle goes like this. This circle has been assigned to this geometry. How do we know? Well, it's not shown here. We had here, section number 1, which we just created, or assigned to this geometry. Okay? So sometimes we can assign a different section. For this much, we can assign circle. This much, we can assign the rectangular. You can vary section along this line. So this is how we generate. And now, last step is the applied load. Okay, applied load. We have 11, and this one, which I already explained. Now, here, what is M1, 2, 3 and F1, 2, 3? What is this? As you can see above, this X is along the line. And F1 is the axial load, and F2 is a vertical transverse load, and F3. And moment 1, moment 2, moment 3, what is moment 1? That's a torsion, right? Because this is the line, and we apply it this way. It's a torsion. And what is M2? Bending. And this is another bending. So M2 and M3 is a bending, but M1 is the torsion. This is how you apply a torsion. Okay? Okay, this is how you apply the torsions. And also, please pay attention to unit. This is a megapascal, and this is a meganewton, and so on. Now, this is all information we need to specify. And then click the button. And imagine, again, the sections, thickness, diameter. What was the length? 10 meters, right? How much was the thickness? 1 centimeter. Diameters? Length was 10 meter, right?
Yes.
Okay. So diameter is the half meter, 0.5 meter, right? So this much, and 10 meters is from here to there. And it's made of a steel. You can imagine how big. And then how much torsion we apply? 1 mega Newton meters. You as an engineer always try to feel the magnitude, the value. What is a 1 meganewton times meter? Torsion is always force times distance, right? So let's say it's a 1 meter and apply the vertical, so it causes a twisting. So 1 meganewton you apply, right? 1 meganewton. What is a 1 meganewton? How much? In terms of a kilogram, by weight, it is a 100,000 kilogram, right? So in terms of a ton, 100 ton, right? So 100톤을 이게 있으면은 1m 떨어진 데서 이거를 이렇게 해서 100톤을 눌러서 이걸 트위스팅 한 거죠. Right? So it's important to understand by numbers, and we as engineers, rather than just no attention. So now this is the solution. Well, looks like a trumpet, huh? Why look like this? I will explain. And importantly, this is the almost, I will try to copy. So what we like to calculate is the how much it rotates, and also how much shear flow or how much shear stress. That is the one we want to compare and conform with our solutions. The topic, that's the one we studied, right? So okay, this is the one we got as displacement, right? And now another one. Now I'm going to explain why the size of circle is increasing. This is just a geometric representations. When we talk, this is the I'm going to use it. When we apply a torque, even though this is a circle, and this one, let's say this is a rotate this much. This is a U theta, right? No other deformation, only U theta. So for when we have show this geometry, we always use here is a scaling factor. Scaling factor is to magnify, make it look big. as you can see here, this is the undeformed shape, and this is a deformed shape. But why does it look like this? That's the one I'm trying to explain. Do you see inside? That is the undeformed shape, and that is the deformed shape. The reason, again, why it look like this is that if you look at this and it looks like this, and all the deformation U theta, and then we multiply the factor alpha, and then original positions, and plus this is a new positions. So if we apply alpha like some value, and this looks like over here, and this one looks like over here, and over here, and over here. So it looks like looks like a bigger shape. Well, this is not just from our tool. It happens everywhere. But as long as you understand what does it mean, it means that it's not because of a larger, it's just because of it's rotating, and then it moves. Okay, it's a little bit annoying and not, but there's nothing we can do about it. Okay, so anyhow, this is a displacement. Another point is that very important is you have many data, but let's call post data or E theta. Let's go to post data. It's the same thing. Post data is a value at the point. Point is a all the point. Do you see that? All the point. This is the value, and all the E stress is element stress is the value. I'm sorry, it's not quite clear, but you have a number in blue. This is element value. So it's not much difference. You don't need to pay much attention to that. So here, just select the post data, and there is a N1 and N6 and so on. Just select N6. This is the shear flow. N6. What is N6 and definition? Why? It looks like all different value because of different color, right? But I'm gonna zoom this value and see their value is pretty much same. So if they are all same, from the blue to red, it looks like this, but as you can see, value-wise, pretty much the same. Okay? So this is what we have, and let's try to get the analytical solution and compare with this solution. That's what we would like to do today. Okay, so first of all, we want to know U theta, but U theta is this is the radius R, and this is the U theta, but we know that this angle of rotation phi is a phi times R, is it? That's the one, phi times R. How do we calculate the phi? We remember T, L, G,
I, J.
J. This is the one we learned. Now you will see what really means. Okay? This is the one, and this is the angle of rotation. And in terms of displacement, and this is the color we just saw that. Now another one is that when you have this torque T, and I'm trying to have a little bit of a thickness there, and magnify here, and like that. And here we do know that there is what? Shear flow, right? Shear flow Q. shear flow Q is what? Remember these solutions? T, simply EA. I mean, not EA, 2A. So this is a torque divided by twice times A. Very simple. But let's try to compare that. So what is this A? You need to be careful. Sometimes we confused with this. This is A? No. A is total A, right? This is the A. So A is simply, this is the A. What was R? You remember? Point 0.25, right? 0.25 millimeter, that was R. And what was L? 10 meter, right? So what else do we need to see? Everything is okay, but we have to know G and J. What is a G? What is E? Remember, this is made of steel. So E is what? 200 gigapascal, right? So what is a G? What is the shear modulus? We cannot remember, but we do know this relation, right? So Young's modulus divided 2 and 1 plus mu. What is a mu? Poisson's ratio, 0.3. So that is okay. Now, last one, what is a J? Polar moment of inertia. Polar moment of inertia. So this is a 2 pi over 2 and R0 4 times Ri 4 times, right? So what is R0 here? R0 is outside radius and Ri is inside. Well, I don't know. We just say 0.25. So 0.25, let's assume this is the average radius. Average radius means that just a this is center, okay? So R0 will be, we just say R plus T over 2. And Ri will be R minus T over 2. Is it okay? So we do have everything. Where is a T? Oh, we don't have a T. T is what? Thickness. How thick was that? 1 centimeter, which is a 0.01 meter, right? Okay? So now we have everything. One more thing is that this is a shear flow. Shear flow is what? This is a shear flow. Shear flow is always, we can say, shear stress times thickness, right? So shear stress is the one we need to calculate. And now at the last step, what is the shear yield strength? We need to know, right? Man, so many things, huh? But every step is logical. So this one calculated from yield strength. Yield strength of steel. What is the value? Yield strength. Well, we don't know, right? Then what do you do? Ask Google. So go Google and strength of steel. And it tells you about all the tensile strengths of. So Google is your friend who has everything, who knows everything. So here you have a steel and so many information. So let's pick the steel. Even steel, you have a mild steel or alloy steel. Say here about 2000 megapascal. 2000 megapascal. What is that? In terms of giga, it's 2 gigapascal, right? What's the modulus? 200 gigapascal. Strength is 2 gigapascal. Am I right? 200 giga, 2 giga, in terms of ratio, percentage, how much percentage is? 1%. Strain is 1%. So it's a strain and stress, and you have a curve. This is a slope, is a 200, and this is a 200, this is a 2, then this will be 1% strain. So it's not easy to remember all the strengths, but easy to remember a strain. Strain is a dimensionless. So 1%, 2% is very easy to remember that, right? So plastic, well, we can easily guess about 2%, 3% is the failure strain. So as long as you know the stiffness, you can easily guess this one. Okay? So anyhow, let's get back to here. And yield strengths. Yield strength is about what? 2 gigapascal, and that is the 1% strain. How do we calculate yield strength when we have this shear stress? What do we need to do? More circle, yes. And Van Misses failure criteria. Now you can see why we have to go through equilibrium. Equilibrium is solved by all these 3D beam and stress and strain relation and geometric condition. Means that we hold it and apply force, equilibrium, get the stress. Once you get the stress, what do? Compare with strengths, right? So all this procedure is a very standard procedure for design any structures. Okay, so this is the step we went, and then now let's get a value. Let's get a value. Value means that all the value here, I will just get a copy. Get back here and get some, calculate the real value and see whether this one makes sense or accurate. Okay, so let's start. We need a radius, we need to length, we need to Young's modulus. What else do you need? We need to, input data. Input data. Thickness. What else? Poisson's ratio, okay. And yield strength S. Well, I guess that's all you need to have, right? So let's define this guy. Define as a name. It's always good to define the name. And as I said, I always prefer to have a color in blue, or better blue here. So let's say we have a radius is what? 0.25. Length 10. Oops. 10. Oh, one is missing. Torsion, right? Torsion. How much torsion we apply? 1, right? 1. well, that was 1. Okay, and thickness 0.1, right? Meters. No, 0.01, right? And Poisson's ratio 0.3, and tensile strength. Now let's convert into all Pascal and all meters. So this one is a 2 giga, which means a 2 giga, right? And this one, oops, Young's modulus is a 200 giga, right? Okay? Okay. Oh, why did I? Length was 10 meter? Okay, 10. Now, we need to calculate intermediate value. Let's say shear strength is a shear strength. I don't want to go through all detailed equations, but this shear strength is you can say this one divided by 2. There is a theory. We will get back to you later, okay? Or if we use the Van Messer's theory, this is a square root A3. I will use this one. So this is a 2 giga, and shear strength is a 1.15 gigapascal. Now, what else do we need? We calculate the shear modulus, right? Shear modulus, and this will be a Young's modulus divided by 2 divided by 1 plus a Poisson's ratio, right? So this is the value. Okay, so this is the shear modulus. Now, what else do we need? We need area. Area is what? Pi, radius, right? So this is okay. I don't want to make a... So, okay, this one, area, and what else do we need? We need to have polar moment of inertia, J polar. How to calculate that? Pi divided by 2 times Ri and Ri, and R0 and Ri, right? So R0, which we didn't define yet, but we will, Ri and 4. Is okay? Okay. Now, R0 and Ri, now you can say this one is what? Radius plus thickness divided by 2, and Ri, the thickness minus, okay? So we give a all name. So this one, now you got the polar moment of inertia. Okay, so let's really calculate the output now. Here, as you can see that the displacement is a phi times r. What is a phi? Phi, and the angle will be a torsions. So torsions times length divided by G modulus. Oops, where is it? Shear. Okay, this one, right? shear modulus divided by polar moment of inertia. Okay? So enter. This is a phi. What will be the unit? Radian, right? This is angle, right? Radian. Now displacement. Displacement is in theta directions. Okay? Theta directions, and this will be simply and this guy phi times what? Radius. So look at this value, 3.3. Now here is a 3.07. There's a 10 to the 2 and 10 to the. So now let's get back. Torsion we apply so 1 what? Meganewton. So actually this has to be 1 meganewton, right? So this is the a Newton times meters. Now U theta, huh? Oh, it's 1 mega, right? So this one is a 0.03. So this is a 3.0, right? It's not accurate, but this is the one. Okay, so this is the a 3.3. This is a 3.0, about 8% error. Okay, this is we call error or difference. Now another one is that what do you want to calculate? Shear flow. Shear flow. How will you calculate the shear flow? Torque T divided by what? Area, right. And then this is the one. .55. This is a 2.5. And this is the A6, means that sorry, a little bit confusing, but this one is a shear flow comes with the same unit as here. See, the unit we apply was 1, right? So this one, unit-wise, this is the same unit as you applied. So 2.55, and this is a 2.51. So when you read this one, okay, I'm going to this way, and when you read this one, is you need to multiply mega. When you read this one, understand you need to apply what? Mega as well. Oops. Well, you have to. Okay. So this one is the 1, and this one is the. Okay, so this is a 1 mega. Okay, how to make it consistent? So this is a 1 mega. We applied the shear flow. We got is a 2.55. This is what? Mega. Remember the shear flow, the unit? Mega Newton per meter, right? So actually, stress it has to be like that, but it's multiply the thickness. So, so this is the one. Okay, so as you can see here, this is a 2.51, this is a 2.55, and you can quite feel confident about this results. let's try, okay, let's try, say this, a magnitude 2.07, and this one is the, okay, I will just say like that, okay? So this is a displacement 0.3, and this is the, so what would make this solution and this solution is a better match, better accuracy? Divisions, okay? Division is the one we can try. Okay, let's do that. So let's go to divisions, and here, well, I think 20 is okay. Let's try to increase the 30. Okay, so let's generate it and then see how does it change. Okay, now it looks much smooth, but we don't know yet how much it will affect solutions. And geometry, it was a 21? No, it was a, I thought this one was a 10, was it? Okay, so this is the one, and now we it's a little bit, and here is 11 and 10, and okay, so let's do that. And by the way, I would think that this 1 centimeter and this is not quite thin enough. I think that could be a reason why we have a little bit of a difference, but let's see what the information we get.
교수님, 아까 리셋하고 material flow 그 단위가 다르게 나오죠.
그 단위가, 그러니까 스트레스는 지금 메가로 나오고 디스플레이스먼트는 미터로 나오고 있지. 아, 그거를 조금 컨퓨징한데 저를 좀 프로그램을 좀 바꾸긴 해야 되는데. See, it takes a little longer. Another one, when you run this 3D beam, if you open other worksheet, such as this one, it takes much longer. So when you run the 3D beam, you better close other worksheet. Then the solution will be okay. So solution is still 3.03. It does not change much. That is the see here 3.07. It does not affect much. So I guess that's not main reason. I think the main reason is this a laminate information. Let's try to, just for the purpose of a comparison, let's try to have a much thinner because the theory we are using is the thin wall shaft theory, right? So let's try to use this one, and then 그랬어? Really? 그럼 그게 이유인가? 맞다. 그게 이유일 수도 있겠네. 어디 갔냐? 이게 아닌데? 여기구나. Yes. So accuracy-wise, much better now, right? Okay. Thank you. But if we increase the decrease, the accuracy will be better because all the theory we are using is based on the thin wall shaft. Okay. So just for the purpose of, so we cannot say which one is right or wrong because this finite 3D beam has its own theory. And the analytical solution is also theory. So try to have a same match. But I think the thinner will make a little bit better. But I think main reason was the this Young's modulus. Okay, now this accuracy is good enough, right? Now it's good enough. One very important point is that how about the shear flow? How come it does not change? Let's say we change this one to a 1000. This shear flow does not change, right? Because this one is just from equilibrium, and this is the atypical case of statically determinate. So anyhow, that is one thing we can confirm. Okay, so I will try to save this one and upload to okay. Very good. So now I'm trying to assign homework, okay? You just got this Excel file, but this is just for the purpose of how to compare that. But all the theory, now this homework will assign you about how to define the case for the 3D beam and how you calculate the analytical solution and compare that. Okay, that's one of the main things, especially for the thin wall shaft. So I do already send you this homework, right? Today, this is the homework. Today's task 7. We have a shaft, circular shaft, and radius and thickness and material you choose. Each group can choose. Now, only difference is that the length, and there is in the half, you apply another torque, T1, another torque at the end, T1 and T2. So calculate a displacement and shear flow, and using the torsion theory, thin wall shaft theory, and 3D beam. Okay, and compare. Is doable? Is clear? Okay. Now, second one, exactly same. Use the same value. Don't change. If you use the 10 meter, you use the 10 meter here. I mean, each group, you don't share the data, but in one group, you better use the same T1, same, use the same, except cross section is a box beam, is a rectangular. Okay, the size is a twice of R. This is just R. This is the same thickness. Only difference is the shape. That's the only difference. Same material, everything same. And this is the torsion theory and 3D beam theory, and compare. Not compare. Why? You don't have any torsion theory. Do you have it? I mean,
No.
I will repeat. The question mark is that this is a box beam, right? So box beam, you can use a thin wall shaft theory. You know the thin wall shaft theory, not the regular torsion theory. Thin wall shaft theory, you can use you can calculate the shear flow, right? Shear flow is okay, and you can a angle of rotation. You remember how you calculate the angle of rotations in thin wall shaft? I should have used that one, but I didn't. Where is it? Okay. Remember this? This is how you calculate d theta dz for thin wall shaft. This will be the same as the TL over GJ when it's a circular. But if it's a non-circular, then you have to use this one. Understand? Okay. Do we have a time? I'll just go to. This is the one we need to calculate. Okay, what is a shear flow? We have a shear flow. We have A and d theta dc. Let's try to calculate that one. Here, shear flow. Oops. This one, shear flow divided by 2, and where's A? A here, right? And times, now integration ds over gt. What does it mean? What is the integration? Along this circle. So this will be along, what does it mean? 2 pi r. This is along circle. Why? GT is a constant. Is it clear? Okay. Now divide by G. What is a G? Shear modulus. And divide by what? Thickness. See, remember this. What is this? This is a d theta dz. So you need to apply what? Length. Then you get the angle. So you need to multiply what? Length, right? Now this is the angle. Now what do you need to multiply for to calculate? Okay, that cannot say much. But here, this is a AD angle. So this is the angle. And where is the phi? Phi. See, this one, remember this was the radian, phi, right? And you see this one is a radian, it's exactly same. The equation we used was a torque, length, shear modulus, Gj, right? J is a very complicated moment of a polar moment of inertia, but this one is the from this theory for thin wall shafts. Okay, so this one is from. Okay, I need to hurry. From a thin wall shaft theory, which is a very important. Okay, I better send this one to you. Okay, so each group will have this one. I can send to all of you. Well, very difficult to find. So anyhow, I hope it's clear to you the group task and how you calculate, how to use 3D beam. And when you apply the torque, not only N, remember you have to have a node and you have to like stress. Okay? 빨리 와봐. 이게 왜 배터리가 안 되냐? 야, 이 친구가 이것만 꽂아놓고 이걸 안 꽂아놨네. 이게 저기 안 되면은 오케이. 됐어. Any questions? Okay, so I